Hey everyone, and welcome. Have you ever looked at an algebra problem, just a bunch of x's and y's, and wished you could actually see what was going on? Well, you're in luck. Today, we're going to pull back the curtain and show you the secret story behind one of the most basic things in algebra, the straight line. Let's jump in.
So what if I told you that a math formula isn't just a random string of symbols? What if it's actually a set of instructions for drawing a picture? That's the huge idea we're going to unpack. We're going to take these abstract formulas and turn them into simple, visual shapes. And it all kicks off with one fundamental rule. Before we can start drawing, we need to know the rules of the game. And in the world of algebra, the main rulebook, the absolute foundation for everything we're about to do, is a concept called a function.
So, what on earth is a function? Honestly, just think of it like a super reliable machine. You put one number in, we'll call that x, and it spits out exactly one number on the other side. That's your y. Every single time, no exceptions. If you put in a 3, you can't get a 5 1 minute and a 10 the next. Nope. One input, one single, unique output. That is the golden rule.
And here's what that rule looks like in practice. On the left, you've got that perfect one-to-one deal. It's predictable. It's reliable. That is a function. But on the right, it's total chaos. One x might give you two different y's, or maybe nothing at all. That is not a function. And for what we're doing today, we need that reliable, one-to-one rule to build our beautiful straight lines.
Okay, so now that we've got our main rule down, let's meet the star of the show. This little equation right here, y equals ax plus b, this is it. This is the secret code, you could even call it the DNA, for every single straight line that you could possibly draw on a graph.
Now, to really get this code, we need to understand a simple move. It's called a parallel translation, which sounds kind of fancy, but the idea is super simple. It just means sliding something around without turning it or changing its size. You know, like pushing a book across your desk. That's it. That's a parallel translation.
So check this out. Here's how we use that idea. We can start with a basic line. Let's say y equals 2x, which goes right through the middle of our graph. Then all we do is add a plus 5 to that equation. And what happens? The entire line just slides. It translates straight up by 5 units. The angle, the steepness, it's all exactly the same. It just has a new home.
So that secret code, y equals ax plus b, it actually holds two separate instructions for our line. You've got the a part and you've got the b part. Let's crack this code and see what each one is telling the line to do. First up, we've got a. We call this the slope. And this is all about the line's direction and its steepness. You know, is it a gentle little hill or is it a super steep mountain? The slope, a, tells us exactly that. It's basically the instructions for how far up or down you go for every single step you take to the right. And the rule here couldn't be simpler. If a is a positive number, the line is going to be climbing upward as you look at it from left to right. But if a is a negative number, the line is heading downward. So just by looking at the sign of a, you instantly know if you're going uphill or downhill. All right, next up is b, which we call the y-intercept. And if the slope a tells us the direction of our journey, then b tells us the starting point. It's literally just the spot on that vertical y-axis where our line gets its start. And changing this b value is what causes that sliding motion we saw just a minute ago. A +1 in the equation means the line crosses the vertical axis up at +1. A -1 means it crosses down at -1. The steepness, our slope, doesn't change one bit. We're just moving the whole line up or down. Okay, we've cracked the code. We know how to take one equation and draw one line. But now it's time for the big reveal. This is the moment where the abstract world of algebra and the visual world of geometry come together in this really cool, amazing way.
So let's start back in the world of pure algebra. Here's a classic problem you've probably seen before, a system of two equations. The goal is to find the one single value for x and the one single value for y that makes both of these statements true at the same time. Now you could solve this the old-fashioned way, but there's a much cooler way.
And here is the secret. Each of those equations is the code for a straight line. So what happens if we draw both of them? Well, the single point where those two lines cross paths, that point is the solution to the algebra problem. The answer is literally hiding right there in the picture.
And would you look at that? The two lines cross at the exact coordinates 3, 2. What does that mean? It means the solution is x equals 3 and y is equals 2. You can go back and plug those numbers into the original equations and you'll find they work perfectly. The place where the picture comes together is the answer to the puzzle.
You know, this whole connection actually shows us there are three things that can happen. If two lines cross at one point, you've got one unique solution. Makes sense. If the lines are parallel and they never, ever touch, well, there's no solution. And if it turns out both equations are just two different ways of describing the exact same line, they're on top of each other, which means there are infinite solutions. The picture perfectly explains the algebra.
So let's just quickly run through the key steps of this whole story, from a boring old equation to an awesome, meaningful picture.
The story is actually pretty simple, right? We started with that one core rule, the function, which makes sure our pictures are predictable. Then we use that rule to crack the secret code of a line, y equals ax plus p, learning that a sets the steepness and b picks the starting point. And then, the real magic happened when we saw that the spot where two lines cross is the hidden answer to an algebra problem, basically turning that problem into a treasure map.
And that brings us to one last thought. This stuff isn't just about numbers and graphs on a page. Think about it. Predicting how much something will cost, tracking growth over time, figuring out your speed on a trip. Now that you can read the secret story of a straight line, where do you see these stories playing out in the world all around you? Thanks for watching.